Рекорд.
Мгм.
Да, во-первых, я хочу всех поприветствовать, кто присоединился к нам сегодня. Я очень рад, что мы смогли сегодня здесь все собраться. И, конечно же, отдельно я хотел поблагодарить Алексея за то, что он нашел время достаточно ранее, чтобы к нам прийти и рассказать про достаточно специфический топик, который касается алайнмента моделей. Вот. Я очень рад, что у нас есть возможность, скажем так, пообщаться с людьми, которые стоят на острие и науки, и практики. Вот. И надеюсь, что будет всем сегодня интересно. Если будут какие-то вопросы, вы можете задавать их в чат в Zoom. Я думаю, это наилучший способ. И, наверное, будем отвечать уже в самом конце, после презентации, чтобы не прерывать флоу. Вот. Также, поскольку мы на записи, убедительная просьба проверить, что у всех выключены микрофоны и нету посторонних шумов, чтобы просто не мешать тем, кто будет потом смотреть. Floor is yours. Можете
Мгм.
начитать.
Да, всем доброе утро, добрый вечер. Я буду делать презентацию на английском, потому что я все это уже тут учил на английском. А вопросы можно задавать на любом языке, на украинском, на английском, на русском, как кому удобно. Okay, so my name is Oleksii Kuchaiev. I'm director of applied research here at NVIDIA, and our team is working on AI model alignment. And today I will be talking mostly about language model alignment. So we will skip multimodal models for now. So this is an outline of my talk. I will start with a quick large language models introduction, and then we'll jump into the topics of model alignment and basically how to do this alignment efficiently. All right, so let's a quick recap on what is meant when people talk about foundation large language models. So this term foundation model was, I think, proposed by the Stanford Human-Centered Artificial Intelligence Group in their 2022 paper. And basically what it means is that it means we train a single model and use it for various applications, as opposed to training different models for different tasks. And we call such a model a foundation model. So why is this all excitement about this foundation models? Well, first of all, before those models kind of appeared on the stage, a few years ago, like the previous way of doing machine learning was, especially in NLP, was you would have like one model per task, right? And if you have many tasks, like if you have, say, named entity recognition, machine translation, sentiment analysis, you would have a separate model per separate task. And moreover, you would need to sort of maintain supervised training data. And supervised, when you say supervised before training data, it means expensive training data, right? Because somebody needs to provide the labels for that data. So, and you would need to kind of collect supervised training data for all of those models. So whereas now with this like foundation models allow us to do basically have to like one model that can learn all those tasks. That model is typically has a rate 0 and few shot learning. I will talk about what that means. And it also exhibits certain emerging abilities, which is which is just interesting from like scientific perspective. Yeah, so let's kind of define what zero shot and few shot learning means, right? So zero shot is like suppose I'm interested in doing like a reviews classifier, right? So instead of training a separate model, I can actually just ask a model like ChatGPT, for example, like using a very human prompt, to actually classify a review, like in this picture, like in this example, right? And models can do this. So the reason it's called zero shot is because the model was never trained to explicitly to perform this task, right? So it just is able to do it. Few shot learning is very similar, except as compared to zero shot, you would just like prepend several, like, I don't know, 5 or 10 examples into your prompt above. And this typically boosts model's performance, right? So again, notice in both this first case and second case of few shot learning, there is like no gradient updates happening, right? So even though it's called learning, nothing is actually being learned. We are kind of just steering the model to do what we want. And there is like whole emerging craft of prompt engineering, which kind of means composing great good and zero, excuse me, zero and few shot prompts. By the way, I do think this prompt engineering is kind of becoming less and less relevant as we align model better and better, right? So we will see why in few slides. So GPT, like OpenAI published this GPT-3 paper, right? So, and the reason why it got everyone excited is that it basically demonstrated this glimpse into this like scaling laws. Basically on this plot, what we see is that on the x-axis, you have model size in, billions of parameters. And what they show is that as you increase model size, accuracy, and this is some sort of average accuracy across many tasks, it actually increases both for few shot, zero shot, like one shot. Actually, this is a bit, I would say, not very correct comparison, because what really matters is not the model size on the x-axis, but more of like training flops. Like flop means like floating point operation, right? So what it means, what really is happening here is that the more you use, the more like compute you spend during model training, like, and the more data it sees, the better performance is. It's not really the model size. Model size just like, it's correlation, it's not causation. Because now there are models that are, I don't know, 70 billion, which is like much stronger than GPT-3, which was 175 billion. So what really matters is how well you train your model. I mean, of course, size also matters. There are actually pretty well-defined scaling laws, which we'll see in a few slides. So what is emerging abilities, right? So I also mentioned emerging abilities. So emerging ability is an ability which appears in larger model, but is not present at a model in a smaller scale. Again, probably it's a like paper from 2 years ago, right? So it's probably what really matters is like amount of training data and compute spent rather than just size. But yeah, what you can see here is that the red dotted line, it's like a random performance. So again, we're just doing large language model training. And for some tasks, like here is a bunch of tasks, like 8 tasks, nothing is like, basically the model performs as well as random on those like tasks. And then suddenly it's unexpectedly sort of shoots up, right, as model size increases. So this is like a very surprising phenomena. I don't think that paper gave a good explanation for it. In fact, I saw another paper in Neurips this year saying that this is like actually a mirage and more of a experimental setup thing. So yeah, it's still an open question if this is actually real or not. All right, so this is a quick overview of like a landscape. I didn't update it with this year yet, but basically from 2018 to 2023, this is like I would say notable open and proprietary models. So as you can see, like when Google published their transformer paper, which is like attention is all you need, this is the title of the paper. A lot of progress, very rapid progress in language modeling has been made. A lot of models have been open source from Google, OpenAI, Microsoft, etc. Then a bunch of models appeared that are, OpenAI stopped being open and kind of started doing everything in the like kind of closed source. We trained the 500 billion model, 500 billion parameter model in end of 2021 to basically demonstrate the limits of scaling training of those models. And then Meta, like around 2023, really kind of did a lot of good work on like open sourcing great like Llama 2 models, which are open source. Open source means like the weights are available on like Hugging Face for everyone to try. What's one notable moment here, like sort of singularity here, is the ChatGPT. The models before it and the models after it actually differ very substantially, and that difference is model alignment, which we'll talk about. Quick explanation on how do we what we do before model alignment, right? So how do we actually train those foundation models? Well, the training loss is actually straightforward, right? So what you see the formula here is like suppose y1 etc. ym are your tokens of your text, and what language model does is that basically it predicts conditional probability, which is expressed like this, right? So which is the sum of these conditional probabilities. The way to think about it is that it's basically a giant autocomplete, right? So it reads a sentence, like for example, it would read from the Wikipedia, like United States of America, etc., and then if it reads like all the way to this like a word federal, and the target would be to predict word district, and it does it actually for every token, right? So yeah, effectively giant autocomplete model, but what's notable here is the scale, right? So we literally train it on trillions of tokens. To give you some perspective, Llama 2 has been trained on 2 trillion tokens. I think Mistral models, if you are familiar with this, like Mistral 7B and their Mixtral models, they have been trained on like 8 trillion tokens. I think when you are closer to like 20 trillion, maybe like 30 trillion, you sort of start running out of useful tokens on the internet. So this is like that scale, right? So huge amounts of text. Of course, we mean we do a lot of quality filtering, right? So we do want to remove duplicates, right? So like we don't want the same articles appear like a million times in the training data. So yeah, the basic deduplication and quality filtering is done, and 10 trillion, 8 to 10 trillion tokens seems to be like what everybody is doing these days. And yeah, it's something where you actually do need to spend a lot of compute. But fortunately, like I said, labs like Llama, like Meta, Mistral, we also release some of the smaller models that we pre-train on this data. Let me actually skip this and just go straight to scaling loss. So scaling loss, what does this? What scaling loss mean? Actually, OpenAI published something called scaling loss in 2020, and then DeepMind sort of published a correction or maybe clarification to scaling loss. And everybody typically follows DeepMind's laws because they are more accurate. And what those laws mean is that they basically tell you, depending on your compute budget, right? So your compute budget is expressed in floating point operations that your cluster can do. So like suppose you have X amount of GPUs for certain amount of time, right? So you would calculate your compute budget, and then scaling laws will tell you how many tokens you need to gather and what you should set your model size to be so that you get the best performance per your compute spend. This is very different than the question of if my target for deployment, say 7 billion, right? So what do I do to get the best model possible? So actually, that second question is easier, right? You just train model as long as you can. But this one specifically tells you, like, given your compute budget, assuming you can kind of host a model of arbitrary size, right? And assuming again that you can gather as many tokens as you need, like what do you do to achieve the best performance? And yeah, why these laws are not obvious, right? So actually, OpenAI and DeepMind did a lot of great job to kind of empirically establish those laws. Well, the reason it's not obvious is because what people noticed with training large language models, and this is this plot on the left, is basically larger models is actually easier to optimize. So easier, I mean, they are more token efficient, right? So if you plot consumed tokens, like the tokens model saw in the training data, and you plot validation loss, so the models will be basically ordered by size, right? With largest models being like here 43 billion model having the lowest validation loss faster, right? So after seeing 200 billion tokens, 43 billion is like the best accuracy, right? So this means that large models are token efficient, right? But the amount of compute, like the time to get to this point of 200 billion tokens for 43 billion is obviously different than the amount of compute you would spend to get to this many tokens with, say, 2 billion model. Yeah, so basically, for those who are involved in like doing this like large scale runs, scaling laws is what they typically look at. All right, so now let's, this was like a really quick intro to large language models. This is before ChatGPT, I would say, right? So this is before alignment. So all of this is still being done, right? So this is like a first step. This sort of pre-training, the most computationally expensive step, and this one gives you what is called Bayes model. So now what is AI alignment with human preferences? Well, the way to think about it is that the difference between GPT-3 and ChatGPT, like when it was first released is that ChatGPT is basically can be thought of as an aligned variant of GPT-3, right? So you basically take your base model, which is GPT-3, and perform alignment with human preferences, and then you get something like ChatGPT, which got you know, like everybody excited, right? Because GPT-3 was impressive. It was impressive for AI researchers, but ChatGPT is sort of impressive for people who are not involved in AI research. So let me actually give an illustration of what of the difference between Bayes model and aligned model. So what you see, what basically AI alignment, it teaches model to interact with humans using the knowledge it already has. So what do I mean by that? So let's take recently released Google's Gemma 7B model. So this is the Bayes model, right? They actually released both Bayes and Instruct model. So if I ask a Bayes model, what is the capital of Ukraine? It generates me text like this. What is the capital of Latvia, etc. By the way, do you see my mouse pointer?
Yep,
Yes.
I think we do.
Oh, okay, yeah. Oops. Yeah, so basically you can see it will just actually generate me a bunch more questions. It doesn't actually answer my question. Well, this is because this model was trained with the next token prediction loss. It's just a giant autocomplete. If I ask it another like more complicated question, plan a sightseeing tour of Kiev for 3 days. Again, it sort of generates some relevant phrases, right? So it doesn't answer the question. However, aligned model on the right? So this is model called Gemma 7B Instruct. It is based on this 7B text model with alignment applied on top of it. And now you can see that it actually kind of works as like some sort of assistant, right? So if you had like a human assistant, this is like kind of an answers you would expect from him or her, right? So you can see it definitely answers the question about, what's capital of Ukraine, and then it can plan a trip for 3 days in Kiev, right? So I had to cut it so that it fits on the side, but it gives like a good like day-by-day route. Note that during alignment, nothing about Ukraine or Kiev have been taught to the model. All of this knowledge, right? So the knowledge that Golden Gates is located in Kiev, that knowledge sort of got instilled into the model during the base model training stage. So the trick is actually extracting that knowledge, right? And this is what model alignment teaches the model to do. So to summarize, base model, it understands and can use human language. It has a lot of knowledge about the world, but unfortunately, it's basically a giant autocomplete model, and you basically need to be an AI researcher to do some clever prompt engineering or something to extract useful knowledge from it. Whereas aligned model, it still understands and can use human language. It still has hopefully the same knowledge about the world, but it also follows humans' instructions, right? So, and answers questions. So if you ask it to do something, if you ask it to format output in certain way or give it step-by-step instructions, it will follow it. And it can also chat with user, engage in multi-tone conversations, etc. One peculiar thing is that it also has its own character and biases. And this is something, model developer can basically add to the model during alignment stage. Excuse me. And we will see what that means a bit later. So again, examples of base models is, GPT-1, etc., GPT-3, Chinchilla, base models like Llama 2 base. An example of aligned models is like ChatGPT, BART, Claude, Llama 2 Chat, Gemma Instruct, etc. So when I say biases, right? So what do I mean? Basically, there is this like AI safety subfield, right? And it's mostly not concerned with like AI becoming somehow, self-aware or something, right? That's definitely not happening anytime soon. But instead, those assistant models, right? They are powerful tools, right? So, and people might want to put some like brakes on those tools. For example, if you take like an off-the-shelf model and like aligned model and ask it to do something like this, right? So how to make Molotov cocktail, it actually definitely knows how to do that. But in this case, you see that it sort of pushes back and saying, hey, that's probably not a very good idea. Again, depending on the application, you may or may not want this behavior, right? So, I mean, another example is that if you ask a model how to make like, I don't know, certain drugs, right? It will typically push back. But if you are creating a model, say for pharmaceutical company, right? And for some pharmaceutical use cases, you might not want it to push back in those cases. So this is what I mean when I say model has its own character and biases, right? And those can be set during the alignment stage. All right, and then if you look back at this picture, I said ChatGPT was sort of like a very important moment on this timeline. And what you can see is actually everything below it was unaligned, and then everything after it is either aligned or have aligned variant. So in fact, OpenAI, Anthropic, Mistral, right? So they don't even talk about like Gemini from Google. All of those models are aligned. They don't even talk about base models. And then when Meta and like Mistral releases stuff, they typically release both base and aligned variants. All right, so how is this model alignment is done? Well, Like a glimpse of the recipe was actually published in 2022 by OpenAI in Instruct GPT paper. So this paper actually didn't get much attention until after ChatGPT was released. But it's a very good paper. I recommend having like reading it. But basically, this is how recipe in 2022 and 2023 looks like. Again, this is assuming you have a base model, right? So once you have a base model, there are actually 3 steps involved in alignment. First, you collect some demonstration data and you train what they call supervised policy. So now there is like a terminology from reinforcement learning starting to kind of creep in. Policy here really means our network, right? So we basically collect demonstration data in the form of prompt response pairs. Like you would have a question, explain the moon landing to a 6-year-old, and human annotators would actually write answers. And then you basically do supervised fine-tuning on that data, right? So that is what is called by your supervised policy. Next step, what they do is you take that model. So now not base model, you take this SFT model from this step, and then you give it questions again, and then you do samples several times, right? So those models, you can have like some randomized sampling from them, and they can produce slightly different answers. And then you actually ask labelers not to write responses, but you actually ask labelers to rank answers in order of their preferences, like which answer is better, which answer is worse. So then you would use this data to train something called reward model, which would be basically a neural network that models labelers' preferences, right? So you would do this, and after this step, you have a reward model that can take arbitrary prompt response pairs and assign certain reward to them. And then what they do is they run it through something called PPO, which is a reinforcement learning algorithm, which basically uses the reward model you obtained from step 2 to actually train your network, again, which is called policy here, because it's like now terminology from reinforcement learning field, right? So you basically use your reward model to train your policy to behave better, right? So to reflect the preferences learned by this reward model. I mean, ideally, what you want is you want human preferences to be learned by reward model. Now, there is certain information and funny things happening, so some preferences might be lost or misinterpreted by the reward model. This is called reward hacking, and then your model would like learn not exactly the things you hope it to learn. So this happens. It's actually a very hard process to do. So this like 3-step recipe that OpenAI published, it's actually very tough to implement. So again, let's have a look deeper into why we actually have this several stages, right? So like, why don't we just do step 1? So that's a question. Let's look at the training data, right? So in the step 1, the training data looks like this. So the humans are given the prompt, like are chinchillas cold-blooded? And actually this prompt, the response needs to be written by the human. And in this case, it's relatively easy, right? So like an average human would know that chinchilla is a mammal. Mammals are warm-blooded, not cold-blooded. So it's kind of okay for the human to write response like this. But imagine if the prompt is something like explain quantum entanglement to me like I'm 6-year-old, right? Well, I don't know, average human probably doesn't know much about quantum entanglement. So it would be really tough for an average human to write a response like that. So the better your models become, it actually becomes much tougher to write good responses to the prompts because they also become more challenging. So on the other hand, the data we do in the step 2 and data collection we do in step 2 looks like this. It's actually a preference data, right? So you take your query and you send it to a model, and the model produces several responses. And you are now faced with, the rater right now is faced with a easier task. And because they now need to choose which answer they like most. It's not like they have to produce an answer, right? And in general, like in computer science and in mathematics, right? It's much easier to identify the correct answer than to write one, right? So if you are faced with possible solutions, it's easier to check if they are actually correct than to produce a correct one. So basically, the data collection is step 2 is much easier in this task. It's not easy, but it's much easier than step 1. And it's cheaper and it's more scalable. And also, by the way, you can, for some domains, you can actually eliminate humans, right? So because if your questions are about coding, right? So you are asking model to generate certain like pieces of Python code. You actually don't need the human to rank your outputs. You need a compiler with a bunch of unit tests, right? And then you basically rank them by how well they pass unit tests. All right, so this is actually, let me not go into the details of this slide, but this is to demonstrate you that this RLHF with PPO is actually very hard, both conceptually and computationally. So again, the step number 2, where we train reward model, is actually relatively easy. It's basically kind of like a classification problem. But the PPO step itself is really hard. It is implemented in several open source toolkits, like including ours. But what I want you to show here is that let's count how many models you actually need to host and like run simultaneously. So there is this policy network called actor. So this is 1. There is reward model. This is 2. This is reward model from this step. There is a critic network, which is initialized from reward model. This is 3. And then there is value network, which is like 4. So like imagine now you actually have to host 4 models, and then they actually interact in a very complicated way during training. So this is both hard, both computationally, and there are tons of hyperparameters. So it's actually hard to get working. So the question is then, do we actually need reinforcement learning in RLHF? It turns out that there are methods that can simplify the whole picture a lot, right? So we are now getting into like 23, 24 recipes. So there is this excellent paper published by Stanford it's called direct preference optimization. And they say that your language model is secretly a reward model. So their main idea is that, well, we have this preference data, right? So preference data in the form of YW is better than losing YL, right? So what they want is, hey, can we tune directly on preference data without this like reward model and PPO steps? Well, actually, there is an obvious approach to do this, right? So if you have preference pairs, what you can do is you can just throw away all the rejected, like all the YLs, and just do SFT on preferred output from preference data. And the people actually have been doing this. It's called rejection sampling, and it also works, but it has a big drawback, right? So you actually lose negative examples, right? Because you throw them away. And yeah, in practice, it is much less effective than RLHF or DPO. But it does work, right? And it's a straightforward approach. So yeah, so basically what the DPO authors did is they did a bunch of math. So this is like the most math heavy slide I have. But what I want to say is that DPO, it actually has some theoretical guarantees that it finds under certain conditions, which are, by the way, almost never met in practice, you would get the same optimal solution as PPO. So let me kind of actually walk you through some of those equations. So PSFT, right? So this is our language model, right? So it basically given a prompt, which is X. So this is our question. It assigns certain probabilities to various responses, right? And we can sample from this distribution, from this model, various response pairs, and then our data looks like this. So our data set D looks the same as in LHF stage, right? So it's basically a collection of prompt, and then response 1, response 2, and we know that response like YW is better than response YL. Now, there is an underlying assumption that this data is sampled from some distribution P star, and there is a theory called, which basically the PPO relies on this Bradley-Terry model, which assumes that this distribution looks like this. And what interesting part that it has here is a reward model, right? So R star is a reward model, and it basically, if y1 is better than y2, oops, according to the reward model, this R star assigns a higher value to pair x y1, right? Again, R star is because we actually it's not given to us, and during RL fine-tuning stage, during this PPO stage, it optimizes this learning objective, which is written here. Important part here is that you see that the reward model is involved, right? So there is this learned reward model, R phi. It's involved in this objective, and then there is this complicated PPO algorithm. But what the DPO authors showed, with some like theorems and some derivations, that actually this DPO objective, which is written here, it's equivalent to the RL fine-tuning phase, right? So if you are interested in the math details, I would encourage you to check the paper. But the most important part I want you to know from this slide is that if you look at the DPO objective, there is your language model, which is like P theta, right? This is the one that you are optimizing. There is your starting language model, P reference. So the P reference is initialized with PSFT, just like step 1 from RLHF. There is your training data involved, right? So there are prompts, there are both preferred and non-preferred responses, right? So you are not losing negative information here. But the more important part, what is not present here, was like the reward model is actually not present as part of this objective, right? So there is no R in the DPO training objective, which makes it actually very easy to implement and optimize. It's basically actually not that much different from computational perspective from like SFT stage. And like I said, under certain conditions, it actually should result in exactly the same solution as PPO algorithm. And that is assuming you can get PPO working correctly. All right, so there are another approaches, right? So one is from my team called SteerLM. So we published it last year in EMNLP. And basically, this is a variant of SFT. So it does have a reward model, but reward model here is actually a bit more granular, right? So you can control attributes like quality, helpfulness, creativity. So basically, instead of actually, when you ask labelers to rate your responses, you would give them guidelines anyways, right? So they need to know like how would you rank one response over another, right? So, and what people typically do is they give them guidelines, like evaluate based on quality, helpfulness, etc. Right? So we just take those guidelines and try to learn them directly. right? So our reward model actually basically is able to predict all those attributes. And then what we do is we do the second step is we take SFT data, right? So data in the form of SFT, and then we annotate it with this reward model with those attributes. And then basically we do a variant of SFT training where we say, hey, here is the prompt, and here is a response with helpfulness, say 7, right? And then here is another prompt, or maybe even the same prompt, but with helpfulness of 1, and this is response which has helpfulness of 1, which is not helpful, right? So as you can see here, we are not losing any negative information either. There is no expensive RLHF involved, and results are actually, comparable. There are more methods. This is like maybe one of the most active research area in this field right now. There are like tons of new methods. There is like CDPO, KITO, IPO, etc. If you are really interested in this topic, I'd encourage you to have a look at this blog post. They basically did the comparison of some of those methods under certain conditions. I think the conclusion they got is that by tuning hyperparameters properly, they can perform very similarly. So there is still no clear winner, and it's still not clear whether RL from RLHF actually has its benefit. So yeah, that's an open research question. So let me spend a moment describing how do we actually measure the progress, right? So how do we evaluate those aligned models, right? So you would basically run the model like this model alignment, but like whether model A is better than model B. And that's actually a very tough task to do because fundamentally you would need human judgments. Like let's consider this example, right? So how would you judge these two responses, right? So suppose the question is very simple. So who founded NVIDIA? And then model 1 produces response 1, and model 2 produces response 2. Actually, both are correct factually, right? So, but they are different. So, and they are produced by different models. So which one is better? Well, it actually really depends, right? So it depends, and this is, by the way, an easy prompt, right? So it's not like I asked the model to plan a trip to Japan for 2 weeks, right? It's a very simple prompt, and it's not obvious how to rate this. So yeah, so that kind of gives you an intuition of why this evaluation of a line model is very hard. And it also often depends on guidelines, right? So because in one setting, this response number 2 would be preferred, right? So because response number 1 kind of contains information that we didn't ask for. But on the other hand, you might want to, like, under certain other conditions, you might prefer response number 1. So really also depends on the guidelines and like human biases and like application. What people do right now, there is this organization, I think it's from Berkeley and University of Southern California, somebody else. Basically, they run this lmcs.org, and what they have is a chatbot arena, right? So they have and you can try it right now, it's publicly available. So you basically go here, you enter a prompt, and then model A would be producing response and model B producing response, and you are asked to say which one is better. And you don't know which model it is until you click, like which one is better. So what happens is this is sort of like a battle between two models, and then depending on which model sort of wins, they use this EO score, which really is derived from chess, right? So chess players are typically ranked by their EO scores depending on outcomes of their chess matches. But basically, each model will get like thousands of questions like this and sort of thousand battles against other models. And then they would compute something called arena EO score, and they rank model by this. So the leaderboard is also publicly available, right? So you can check it out at this link. And so yeah, this is the one way to evaluate aligned language models. And you can see, currently like some preview variant of GPT-4 is the best, followed by BART. I think today they published Claude 3 models. I haven't checked it. It's probably number 2 or something like that. I don't think it will beat the top GPT model. Yeah, but again, the point is here that the humans are actually doing the judging, right? It's very hard. So fundamentally, humans are involved. Well, you can try to replace humans by the top model from this leaderboard, right? So there is something called empty bench, which everybody can use. It's basically a set of prompts, and then it uses GPT-4 as a judge instead of human, right? So now we are kind of starting, it does have problems, right? But it allows for fast iterations, especially if you're working with models that are like, not not like the frontier models, not like gigantic state-of-the-art models, but something more reasonable, right? So that is a good metric to iterate with. There is also important metric called MMLU, but the MMLU is a general knowledge multiple choice QA task, and this is typically one of the most important metrics for Bayes models. So not for aligned models, but for Bayes models. And the reason why I mention it here is that both EO and empty bench scores correlate very strongly with MMLU, right? So what this really means is that if you want if you want a very great like state-of-the-art aligned model, you actually need to start with a great Bayes model. And the actual alignment algorithm is important, but maybe much less so as the Bayes model from which you start, right? Because there is like a very good you see the R2 square, sorry, R square is very high correlation between aligned model benchmarks and MMOU. All right, so yeah, let me also say a few words on how to do this efficiently. Those large language models, by definition, they are large, right? So it means a lot of memory, a lot of compute. And actually, for the interest of time, let me just jump to Aura, right? So I would say there is this method published by Microsoft, like a very important, very influential paper. And it basically shows how to do like large language model tuning much more efficiently, both from computational perspective and from like space perspective. So they introduced this method called LoRa, and this LoRa method can be combined with all of the alignment techniques, right? So you can, if you're doing stage 1 SFT, you can do it with LoRa. If you do DPO or STRLM, instead of messing with like all model weights, you can actually do it with LoRa, right? So this is the way, right? So for someone who wants to try larger models, but they don't have as many GPUs, right? So this is the way to go. And yeah, so again, the paper is here. If you haven't read it, I really recommend this paper. All right, and so this is my last slide, right? So some of the, because I thought this is a, maybe kind of academic audience, right? So like maybe some of you are students. So here is some resources I would recommend to get started. So in terms of software, something like Olama, again, openly available, works on Mac and Linux machines, actually don't need to have GPUs. Of course, it will be like super slow for larger models to run inference on CPU, but at least it can work. If you do have like Windows and the RTX GPU, you can check out our Chat with RTX library. So this is basically a set of this Olama Chat with RTX GPT-4o. Those are tools to run language models locally and like play with them, interact with them. There are some hosted APIs. So we host a bunch of models like Llama, Mistral, Mixtral, some of our models here at the AI Foundation Models catalog. Again, you can interact with them for free, even call them via API for free. There is, of course, some like limit on number of calls, but you don't even need a registration to do this. Hugging Face obviously has tons of models. It's a sort of a wild west, right? So they are of various quality, questionable licenses sometimes. But there are lots of very, very good models there, including some of ours here too. If you are, working with some GPUs and you want to do training, tuning, and aligning your own models, obviously I would recommend like some of the work from like our teams. Like Nemo is where you can do pre-training, parameter efficient tuning, like or etc. Nemo Aligner, right? So we have a bunch of modern alignment methods like DPO, SteerMM, and like KTO implemented. If you are adventurous, you can try RLHF as well. PPO, it is implemented and it does work. It was painful to do, but it does work. In terms of educational resources, really recommend this series from Andrei Karpasi and like Nathan Lambert. And yeah, and last one, NVIDIA GTC, we have this conference, it's end of March, and you can register for like virtual attendance, and virtual attendance is free. It's more of a like industry, it's not like a directly academic conference, but it will have a lot of great talks. Yeah, and I would be happy to take any questions.
Yeah, thanks a lot for sharing information with us. I think we will like keep chatting in English so that we do not like jump between different languages, and it makes a bit more sense for people who will listen, I think. That was a great presentation. I thank you deeply. I do have a few questions from my side, and then probably other people, if they have any question, they will become more adventurous, as you said, and probably also jump into the conversation. So my first question will be, so you've mentioned that there is a scaling law with respect to the training of the model, right? So do you think there is some sort of alignment scaling law? So do you think it is possible to, let's say, align a model infinitely well, so that we take some small model, let's say, or comparatively uncomplicated model as of future, right? So now it might be some hard model like GPT-4 or something, and we're aligning into something like some sort of AGI type of thing.
Yeah, so that's very logical question, right? So we have scaling laws for pre-training. Do we have scaling laws for alignment? Actually, the authors of Instruct GPT paper. So this is a group led by I forgot his name, because last name is Schulman at OpenAI, right? So who actually is an author of PPO algorithm. They recently published something called scaling laws for reward models, right? So there is this reward model stage involved in some of the, not all, but in some of the model alignment algorithms. They published some scaling laws which basically say, the larger the model, the more preference data you have, kind of how would you scale those simultaneously, kind of similar to pre-training was. So yeah, you can search for that paper. I haven't been very impressed by that paper, to be honest. I think it's a bit too early, so I don't think that it's a maybe basically more work needs to be done there. Now another part of your question is about like infinitely aligning, right? So if you forget about, say, reward model scaling was. So what I have seen is actually algorithms like GPO and a lot of like they are very good at doing actually two things at the same time. One is alignment itself, But if your preference data comes from much stronger model, right? So you can actually sample responses again from ChatGPT. And I actually even asked GPT to produce rankings. People do that. So now the algorithms like DPO, they will be actually doing two things. They will be doing distillation and alignment, right? So if you have a strong teacher, that means if you want to have as good smaller model as possible, then this is actually a great way forward, right? So you can use your large teacher and distill it like very well into a small model, and you would get like amazing. Like I think on that MCS leaderboard there is this Starling model which gets empty bench of over 8, and it is only 7 billion model. So it's basically was aligned in such a way with distillation and alignment. Now aligning all the way towards AGI, I like to say that you can't achieve that just with alignment. What you need is pre-training as well, because remember, model actually gets all the knowledge uh, during pre-training, and alignment is about actually teaching new behavior. So, for example, right? So if let's say we teach a model like we finished pre-training recently, right? So and now it's 2024, right? And then say in 2025 some like event happened in the world that like I don't know, some president changed, right? So you don't want to change the president, like you don't want to change, like if you are doing alignment in the future, you don't want to give it examples, who is the president and like a new name, right? Because because then you are running into the danger of like teaching model to hallucinate. Like you really want to teach model new behaviors with the knowledge it already has. If you want to add new knowledge or like update new knowledge based on news, based for example on news and something like maybe you got new data, you would just do you just continue pre-training with that data and then do alignment on top of it. So yeah, I think you basically need to do, it's like it's more a question, I guess, into the pre-training stage.
Yeah, great. Thank you. My second question will be, so there is an obvious like question, like what is somehow more expensive in terms of resources, like time and money, to train a base model or to align an existing model. But I think it's also a bit speculative as, different probably companies or organizations, they have different different amount of resources available. So for example, if it's a university, right, you can ask your students to make some sort of comprise answers for free, right, and you will not spend that much money on let's say generating. But another question here is that we do know that, especially when the ChatGPT came out, people were trying to kind of break the alignment, right, and generate some sort of answers that were not supposed to be generated, right? So as in your example with Molotov cocktail, right, or to do something that we like people were not supposing the model will do. So do you think it is possible to kind of align model like with 100% robustness, so that there is no way you can engineer a prompt if you do not have access to the weights and stuff like that, right? So that's too much to ask. But if is it possible to align the model so that you cannot break it with a prompt or a sequence of prompts? Or we will always be in a situation where there is something unknown that can trigger a behavior we don't want the model to actually show us.
So yeah, okay, you actually had two questions in your question, right? So first about pre-training versus alignment in terms of cost. Again, pre-training is like 1,000 times more expensive. Let's put it this way, right? Because again, we are talking about 10 trillion tokens. So that basically means literally thousands GPUs for months, right? But during alignment, you would, I mean, like you can start with as little as like 1,000 prompt response pairs, right? So, and basically, like you mentioned students, right? So like some of the resources I have here, right? So if you have just one GPU, right? So if you have, I don't know, like just one GPU, what you can do is you can go to some of those like Hugging Face Hub, right? So grab, I don't know, Gemma 2 billion or Gemma 7 billion, depending on your GPU size. Like I said, you can use LoRa, and then you can actually attempt like instruction tuning, like SFT or DPO on single GPU with a model like that, right? So, but I mean, it wouldn't give you a state-of-the-art model. Actually, depends, right? So maybe for your use case, right, you need to be creative if you are constrained on resources by resources, right? So maybe you can align it very well for like a very specific task. So yeah, alignment is doable. Like pre-training, probably unless you have, you know, thousands of GPUs, you shouldn't like engage in it. Or maybe, but alignment, yeah, especially with parameter efficient methods like LoRa. Uh, Now your second question about is it possible to align it 100%? I say I don't. My personal opinion is no, right? It's still probabilistic models. All of this is still probabilistic. Uh, but you probably can get very high, very close to 100%, right? So it would be, I don't know, 99.99. Like try jailbreaking GPT-4 or Claude 3. Those are very strongly aligned models. Like you would have like really hard time to get them produce Molotov cocktail recipe or something like that. Uh, it does have but aligning them such strongly does have this downside, right? So like sometimes, like especially some of the Llama 2 chat models, they are over aligned. So it is possible to, you know, do too much on the safety side so that models like refuses to tell you how to kill a process in Linux, right? Because it sees the word kill and becomes kind of scared, right? So uh, yeah, that's a hard trade-off to make. So, and I guess it also depends on what your goals are when you're doing alignment.
Yeah, this actually ties quite well for the next and the last question from my side is that so when we do alignment, actually we can we clearly what would you say, like block certain behaviors, and these type of behaviors that can actually affect the capabilities, including the emerging capabilities of the model. And my question here is, when we align the model, actually we do not know from the very beginning like what like all types of tasks it is capable of performing if we would categorize them quite narrowly, right? So if we would say, okay, to create a schedule for a Japan trip, it's one task, and another task is to create the same schedule but for another country, for example, right? In this case, the amount of tasks is basically infinite for model to handle. And here the question is like, is it how do we know, and whether it is possible to know from the very beginning when we align the model what types of behaviors we are actually not tackling, right? So what areas are not changed when we do the alignment, and where actually alignment goes. It's kind of the same question with fine-tuning, for example, right? So when you fine-tune a model, it is possible that it will forget something, probably something quite important for us, right? But on the other hand, it will learn too much of the new information, right? So is it the same trade-off with alignment, right? It can kind of forget something useful it was capable of, and just align too hard on some new data that you push into it?
Yes, so short answer is yes, and the reason I say yes is because what we do is like when we align model, we look at empty bench and some human evaluation, But we also do run models through a typical suite of base model evaluations like MMLU, Big Bench. There is literally, actually, for base models, there is literally like 100 of benchmarks people run them through. And there are some regressions sometimes, like MMU, for example, 5-shot, like that's actually, and if you think about it, it does make sense, but so something like 5-shot MMU, which is like all base model report, it actually drops a little, right? So it drops like by 1 or 2 points. But 0-shot MMLU is where you are not giving it in context examples. That actually typically goes up a little. So yeah, the short answer is yes. Some of this, I would say, some of the capabilities does seem to deteriorate, especially around things like few-shot learning. But I mean, when you're interacting with chatbot, you are not doing any few-shot learning. You are typically just interacting with it if it were some sort of assistant.
Yep. Thank you. Thank you very much for answering my questions. Probably you guys do you have any other questions? You can actually use voice chat or just type
So there is
something.
one in chat,
Yeah.
right? So a known problem with LHF and other methods and DPL is that you're optimizing against observable misalignment, hence against observability and misalignment. Doesn't human pumping against misalignment. I don't think I understand what misalignment means. Maybe it means that, like what I said about reward hacking, right? So like if we, like one thing, for example, we noticed, right? So like humans do the ratings of the preferences, right? And you really want to like learn some sort of human preferences with reward model. But this being, machine learning, the reward model will just sort of get attached to some correlational properties of responses. Like, for example, if it happens so that the humans on average prefer some longer response because they think it's better, now the model will actually just kind of start predicting every longer response as better, which is of course problematic because then your PPO stage would explode and you may start generating longer and longer responses. So yeah, sometimes what's like this is a preference learning is a tough problem, right? Because it's sometimes you get into the situation where there is a correlation which is not actually your preference, but the model will just attach to it and learn it instead of actual preferences. Yeah, and obviously we are working on, like our group is like a research group, right? So we are trying to solve some of these problems.
Yeah, I think this is it. I don't have I mean I have more questions, but they're rather technical and I don't really want to kind of ask them here and steal more of your time. Yeah, so yeah, he said that he has many questions. So if yeah, here so you said it in chat. So I think Oleksii, do you have any more time for answering the question? So I think
Actually,
yep.
sorry, I'm already 10 minutes late for my next
Yep.
meeting.
Yeah, sure.
I can share my slides if you want.
Yeah,
There's
that would be
nothing
great.
secret.
And I will also, from my side, will share the video recording.